Hi, Assalamualaikum and good day everyone. So today for week 5, I'm going to teach you for simple harmonic motion under part 2. Alright, so for this lesson, I'm going to cover conservation of energy in simple harmonic motion and simple pendulum and spring. As you can see in the figure here, this one is represented by the simple pendulum. Alright. So at the end of this chapter, you should be able to understand the concept and know how to apply formula of energy in simple harmonic oscillator. Alright, simple harmonic oscillator oscillator means that when the object or spring or pendulum in a motion, that's why we call as simple harmonic oscillator. Alright, the second one, understand the concept of simple pendulum and spring. We're going to compare we're going to understand the concept and equation related to the simple pendulum and spring. Alright, let's have a look at the energy in simple harmonic motion. Okay, first of all, we're going to look at potential energy represented by U. Okay, the energy, of course, the unit in a joule. Alright, so then for potential energy that you have learned in part 1 related to the height, but for energy in simple harmonic motion, the potential energy here represented by stretch or compress of the spring, means that it represented by the displacement of the spring. Whether the spring are stretched or compressed, then work must be done. Alright, if let's say the spring stretch or compressed, means that they are work done. Alright, so from here we can find the potential energy of a spring given by U, potential energy, equal to half K is a spring constant, X is a displacement of the spring, whether the spring in a stretch condition or compressed condition. Alright, stretch means that you pull the spring. Compress, as I have learned in previous video, compress means that push the spring. Alright. Okay. Then, if let's say there are no K given, alright, because we know that K from previous slide, from previous video, alright, we know that K equal to m omega squared. How to get this equation? I already shown you in the previous video. Okay, alright, so then we just substitute this equation, okay, into the equation here. Substitute the equation m omega squared. Alright, sorry, m omega squared. M omega squared here is represented by the K. Okay, then simplify the equation m omega squared x squared. Alright, so then x squared here, if let's say the equation of there are no x given, alright, we can substitute the equation of motion of x. If let's say we take equation of motion as a sin, alright, omega t plus psi. We assume that the condition of the equation of motion here at some phase constant. Now, this is a general equation of alright, of displacement with respect to time. Alright. Okay, so then since here x squared, so we just square all the equation here. Square all the equation here. Then it become a squared sine squared omega t plus psi. Alright, so as why we substitute the equation here means that if let's say there are no x given, we also can find the x by using the equation of motion here. So then we have three equations for potential energy in a spring. You have kx squared, or if let's say there are no x given in a x, we can substitute in a k, we can substitute k by using this equation. Second equation of potential energy, and the third equation. It's depend on what problem given and refer to this equation when you want to solve the problem related to the potential energy. So then, okay, potential energy, okay, this one I already showed you how to get this equation. Alright, let's proceed with kinetic energy. Kinetic energy, and of course the unit also joule, because this is related to the energy, and the symbol, the variable is represented by K. Alright, so the kinetic energy of the object in simple harmonic motion is given by K half mv squared. It's similar to the translational motion. energy in translational motion or energy in a linear motion. But now we want to derive this equation by using translational equation here, and then we want to combine with the simple harmonic motion that we have learned in previous video. Alright, this equation from the previous video, and we just substitute the V here, because V here, okay, V here represent the simple harmonic motion velocity. So we just substitute the M, okay, M is same because the mass half is constant. So here is represent the V. Okay, because of squared, so means that we squared all the equation here. So what we got here, if let's say we square the V here, so what we got, omega squared, then there are no square root already because we can cancel out square root with the square, time with a squared minus with x squared. So that's it. So we got this equation. Alright, this is the kinetic energy in simple harmonic motion. Alright, if let's say we want to find the kinetic energy in terms of time, is given by, okay, this one, how to get this equation, I already show you how to get the V. How to get the V here? The V here we get from the equation dx over dt. We differentiate the equation of displacement over time, so we got V. Because of x earlier, we use x equal to a sine omega t plus v psi. Alright, omega t plus v psi. So when we want to find the V, we just differentiate the x over dt, so we got the V here. So then we just substitute the equation of V inside the equation of kinetic energy here, half m omega squared a squared. How to get a squared here? Because V is squared. Alright, we have already see here, refer to the equation of linear motion, the original equation of kinetic energy. M is a constant, half is a constant. Alright, so V squared here, omega squared a squared cos squared omega t plus v psi. Omega here, we just substitute this equation in here, so we got a squared and so on. So we get this equation for kinetic energy. So there are three equations of kinetic energy, half mv squared, or if let's say there are no v given, so we can substitute the equation of v into simple harmonic motion, get the second equation of kinetic energy. Alright, and the third one, when we want to use the equation which related to the equation of motion for velocity in terms of time. So this is the third equation of kinetic energy.